Welcome to Civil Engineering Edge, where science meets strength and design meets destiny. In today's video, we uncover one of modern engineering's greatest triumphs: how reinforced concrete stands tall against one of nature's most destructive forces, earthquakes. From hidden seismic waves to the ingenious partnership between steel and concrete, we'll explore the secrets that keep our cities standing when the ground itself begins to move. So tighten your seatbelt, or rather, your safety helmet, as we journey deep into the engineering brilliance that transforms disaster into durability. Let's discover the seismic resistance secret. Imagine a skyscraper swaying violently during a massive earthquake, glass rattling, walls trembling, but still standing tall when the shaking stops. How does such a structure defy forces strong enough to crumble mountains? The answer lies not in luck, but in brilliant engineering, specifically the science of reinforced concrete. In this video, we lines uncover how engineers design concrete structures that can dance with the earth rather than collapse under its fury. From the physics of seismic waves to the innovative design of our sea frames, you lines discover the secrets that keep our cities standing strong even when the ground beneath us refuses to stay still. The hidden dangers of unseen forces, the fury beneath, earthquake destruction unveiled. The video opens with dramatic real-world visuals: ground fissures tearing through highways, glass towers trembling against the horizon, and bridges twisting like ribbons of steel. The earth roars as if awakening from centuries of silence. Within moments, what once stood tall and proud is reduced to heaps of shattered concrete. Earthquakes are among the most terrifying natural forces on the planet, unpredictable, invisible, and devastatingly fast. What makes these events particularly dangerous is that traditional buildings are primarily designed to handle gravity loads, vertical, steady, and predictable. But during an earthquake, the threat doesn't come from above, it comes from beneath and sideways. The ground shifts violently in all directions, producing dynamic accelerations that interact with the structure's mass. This causes inertial forces, the building's resistance to being moved, to act against the shaking ground. The result is stress, cracking, and, if not properly designed, catastrophic failure. Imagine each floor of a tall building moving in a slightly different direction, lagging milliseconds behind the one below it. This out-of-sync motion, called interstory drift, is what tears joints, buckles columns, and fractures beams. Concrete, though immensely strong in compression, becomes brittle and weak under tension or sudden lateral stress. This is where the true genius of engineering emerges, not in preventing movement, but in controlling it. The challenge is to design structures that can dance with the earthquake, bending gracefully instead of breaking violently. Every tremor reminds us that the ground beneath our feet is not static. It is a living, moving force of nature that demands respect, understanding, and innovation. Understanding the enemy, P waves and S waves. To defend against an enemy, one must first understand its nature. In the world of earthquakes, that enemy is seismic energy transmitted through the earth in the form of waves. When tectonic plates suddenly release accumulated stress, two principal types of waves radiate outward: P waves, primary waves, and S waves, secondary waves. P waves are compressional and travel the fastest, moving through solid rock, water, and even air. They push and pull the ground in the direction of travel, similar to sound waves. While these waves cause initial rumbling and minor shaking, they act as the Earth's early warning, the first whisper of what is to come. Then, within seconds, arrive the S waves, slower but far more destructive. S waves shake the ground perpendicular to their direction of travel, moving it side to side and up and down simultaneously. This motion creates the intense vibrations that make buildings sway, bridges buckle, and foundations crack. The horizontal accelerations induced by these waves produce enormous shear forces and bending moments in structural elements. Engineers describe these effects through the concept of base shear, which represents the total lateral force the structure must resist. The magnitude of base shear depends on ground acceleration, building mass, stiffness, and damping. Heavier and stiffer buildings attract higher forces, which is why modern seismic design favors lightweight, ductile, and flexible systems capable of absorbing energy rather than resisting it rigidly. By mapping local soil behavior, wave propagation, and expected accelerations, engineers use response spectra to predict how different structures will react. It's this deep understanding of P and S wave behavior that allows us to turn invisible, unpredictable ground motion into quantifiable engineering design parameters, the first line of defense in seismic resilience. Turning chaos into stability, the engineering challenge. Now that we understand how seismic forces act, the next challenge is transformation, converting chaos into stability. The question is profound. How can we make concrete, a rigid and brittle material, behave flexibly during an earthquake? The solution lies in reinforced concrete, RC, a brilliant fusion of materials that complement each other's weaknesses. Concrete is exceptionally strong under compression, but weak in tension. Steel, on the other hand, excels in tension and ductility. When these two materials are combined, they create a composite that can resist bending, shear, and torsion effectively. During seismic activity, this combination allows structures to absorb and redistribute energy rather than collapse under stress. But material choice alone is not enough. The secret lies in design detailing, the precise placement, anchorage, and confinement of reinforcement bars. Engineers follow strict guidelines, such as is 1893 criteria for earthquake-resistant design of structures, and is 13,920 ductile detailing of reinforced concrete structures to ensure that every beam column joint, stirrup, and lap length contributes to ductility and energy dissipation. The philosophy of seismic design isn't to make a building unshakable, but to make it safe, repairable, and resilient. By introducing features like shear walls, moment-resisting frames, and confined columns, engineers enable structures to deform in a controlled manner, releasing energy gradually rather than all at once. Furthermore, the use of base isolators and damping systems in modern designs adds another layer of protection, reducing the transfer of seismic energy to the superstructure. Through these innovations, the destructive chaos of earthquakes is transformed into manageable movement, a graceful, engineered response that keeps lives safe and structures standing. This marriage of science, art, and engineering represents humanity's triumph over one of nature's most violent forces. The unsung heroes, rebar and concrete's partnership, from brittleness to brilliance. Why concrete alone isn't enough? Concrete, one of civilization's oldest and most trusted building materials, is an engineering marvel in compression, but a silent failure in tension. Imagine a massive column holding up a bridge deck. Under vertical load, it performs flawlessly. But when lateral forces, like those from an earthquake, push and pull from the sides, concrete begins to crack. Its molecular structure, while dense and rigid, cannot stretch. Once its tensile limit is reached, failure occurs suddenly and catastrophically. This fundamental limitation of concrete was one of the greatest challenges in early structural engineering. Builders observed that when structures faced bending, the lower portions of beams or slabs, the tension zones, would rupture first. The upper portion remained compressed and strong, but the bottom simply gave way. What was missing was a material that could share the load, something elastic, ductile, and capable of handling tension. The solution came in the form of steel reinforcement bars, or rebars. Steel possesses high tensile strength and an ability to elongate underload without breaking. When combined with concrete, it transforms a brittle mass into a composite system capable of bending, flexing, and dissipating energy under extreme conditions. Thus began one of the most successful partnerships in construction history, concrete providing the muscle to resist compression, and steel acting as the tendon to handle tension. Together, they create structures that not only stand tall under everyday loads, but also endure the violent shaking of earthquakes with remarkable resilience. Inside the frame, how rebar strengthens concrete. To truly appreciate this partnership, visualize a cross-section of a reinforced concrete beam. The upper half compresses under load, while the lower half stretches, the perfect place to insert steel. In an animated sequence, the camera dives inside the concrete, revealing steel bars aligned along the tension zone. These rebars are placed strategically where tensile stresses are greatest, at the bottom of beams, along columns, and within slabs, creating a structural skeleton that quietly carries the hidden battle between opposing forces. When the ground shakes during an earthquake, these steel bars act like springs. They absorb and redistribute tensile energy, allowing the concrete around them to crack in a controlled, harmless pattern rather than shatter unpredictably. Engineers design these systems with precision, calculating bar diameters, spacing, anchorage, and lap lengths using standards like IS 456 to 2000 and IS 13920 to 2016 to ensure maximum ductility. To visualize, imagine a bending beam. The top compresses, the bottom elongates, and the rebar stretches slightly, storing energy and preventing total failure. Stirrups and ties wrap around the longitudinal bars, resisting shear forces and holding the cage together. In columns, reinforcement is arranged symmetrically to handle compression, bending, and torsion simultaneously. The beauty of this design lies in its simplicity. Steel doesn't fight the concrete, it completes it. The resulting material behaves like a single, unified system, balancing strength and flexibility. Without this silent steel network hidden within, concrete structures would crumble under seismic forces that they now gracefully endure. The bond that saves, adhesion between concrete and steel. While steel and concrete each bring their own strengths, their true power emerges from the bond between them. This adhesion, a mix of chemical grip, friction, and mechanical interlock, ensures that both materials act together as one. Without it, the steel would slip inside the concrete during stress, and their partnership would fail. The secret to this bond lies in surface design and chemistry. Modern rebars aren't smooth. They're ribbed or deformed, with ridges that anchor tightly into the surrounding concrete. When fresh concrete is poured, it seeps into these tiny grooves, hardening around them to create a mechanical lock. Simultaneously, a thin oxide film forms on the steel surface, enabling chemical adhesion and preventing corrosion. When seismic waves hit, the load is transferred through this bond. As the structure flexes, both materials deform together. The steel elongates, the concrete cracks slightly, and then closes again as the shaking subsides. The rebar doesn't merely reinforce, it controls the cracking process, ensuring cracks remain narrow and non-structural. This bond is rigorously tested in laboratories under pullout and cyclic loading to ensure reliability. Engineers also ensure adequate development length so that the rebar achieves full strength before it could ever pull free. In essence, this invisible connection between concrete and steel is what makes reinforced concrete a living, breathing system, one that resists, absorbs, and recovers. It's this unbreakable partnership that transforms raw materials into life-saving structures. Bridges that flex, towers that sway, and homes that endure when the ground beneath us trembles. Engineered resilience, design principles for earthquakes. Beyond strength, the power of ductility and shear walls, strength alone cannot save a building from an earthquake. Resilience comes from ductility, the ability of a structure to bend, deform, and absorb energy without collapsing. Unlike static loads where strength dominates, seismic loads are dynamic, reversing direction rapidly. Rigid structures may seem strong, but they fail suddenly when overstressed. Ductile structures, however, yield gradually and survive repeated shaking. In reinforced concrete, ductility is achieved through proper detailing and material behavior. When designed correctly, steel reinforcement yields before concrete crushes, creating a controlled, warning-based failure mode. Engineers ensure this by providing adequate confinement reinforcement, such as closely spaced stirrups and hoops, especially at beam column joints. These confine the concrete core, preventing premature spalling and maintaining strength even after cracking. Another crucial feature in seismic design is the shear wall, vertical, reinforced concrete walls that act like the spine of a building. While beams and columns handle localized bending and shear walls resist overall lateral forces. They distribute earthquake loads uniformly to the foundation, significantly reducing lateral drift. When strategically placed around staircases, lift cores, or building perimeters, these walls enhance stiffness and prevent torsional motion. Shear walls work in tandem with moment-resisting frames, balancing stiffness and ductility. A well-designed structure does not rely solely on one system, but integrates both. The walls provide stability, and the frames offer flexibility. This dual system ensures that when the earth shakes, the building sways safely without losing integrity. Thus, seismic design is not just about adding more steel or concrete. It is about crafting structures that understand and respond intelligently to the forces of nature. Controlling failure, strong columns, weak beams, and the soft story solution. When an earthquake strikes, failure is inevitable, but where and how it occurs can be controlled. This principle defines modern seismic design philosophy. Allow energy to dissipate safely without total collapse. One of the most effective strategies to achieve this is the strong column, weak beam concept. In a reinforced concrete frame, beams and columns meet at joints where stress concentration is highest. During an earthquake, bending moments develop. If beams are weaker than columns, the plastic hinges zones where deformation occurs form in the beams, not the columns. This is intentional. Beams can fail safely without leading to a total collapse, whereas a failed column can cause the structure to pancake. By designing columns stronger by at least 1.4 times the beam moment capacity, engineers ensure the deformation remains ductile and repairable. Now, consider the soft story problem, a common cause of building collapse. A soft story occurs when one floor, usually the ground or parking level, has much less stiffness than the floors above, causing it to deform excessively. Engineers solve this by reinforcing soft stories with braced frames, shear walls, or infill walls, ensuring uniform stiffness distribution throughout the height. In addition, engineers employ load path continuity, making sure every lateral load has a direct, uninterrupted path from roof to foundation. Openings, offsets, and irregularities are carefully managed to prevent weak zones. Advanced modeling tools like ETABS and STAAD Pro help simulate how structures deform under real earthquake records. These analyses reveal where plastic hinges will form, allowing designers to adjust reinforcement, stiffness, and damping accordingly. Ultimately, strong columns, weak beams, and soft story correction are just design details. They are philosophies that save lives, ensuring that when disaster strikes, buildings deform predictably, not disastrously. The small details that save structures, splicing, anchorage, and joint reinforcement. Even the most sophisticated design can fail if detailing is poor. The true resilience of reinforced concrete lies in how carefully engineers handle the smallest elements, splicing, anchorage, and joint detailing. Rebar splicing joins to reinforcement bars end to end. If done improperly, it becomes a weak point that tears apart under tension. Engineers maintain adequate lap lengths based on bar diameter and grade, ensuring seamless force transfer between bars. In critical seismic zones, mechanical couplers are often used instead of lap splices for superior performance. Anchorage, the proper embedding of bars into concrete, is equally vital. Hooks, bends, and sufficient embedment lengths prevent bars from pulling out during violent shaking. Similarly, beam column joints are densely reinforced with cross ties and hoops to confine the concrete core. These prevent crushing and maintain load transfer even after cracking. Every stirrup, tie, and bend in a reinforcement drawing has a purpose: to preserve ductility, continuity, and confinement. These detailing measures ensure that localized damage does not cascade into catastrophic collapse. In the end, it's not just design philosophy, but execution precision, the unseen artistry of detailing that transforms blueprints into earthquake-resistant reality. Beyond the blueprints, modern innovations and testing, base isolation, making buildings float during earthquakes. Imagine a building that doesn't shake when the ground beneath it does. One that seems to glide gently while everything else trembles. This is no science fiction. It's a revolutionary technology known as base isolation, a game-changing approach in modern seismic engineering. In conventional buildings, the foundation is rigidly connected to the ground. When an earthquake strikes, ground motion transfers directly to the superstructure, causing violent shaking and internal stresses. Base isolation breaks this connection. It introduces flexible bearings or isolators between the foundation and the structure, effectively decoupling the building from ground motion. These isolators are usually made of layers of rubber and steel, sometimes incorporating lead cores or sliding bearings that absorb and dissipate energy. When the ground moves, the isolators flex horizontally, allowing the building above to remain almost stationary. The entire structure, in a sense, floats on flexible paths, moving gently, safely, and independently from the shaking earth. This technology dramatically reduces the acceleration transmitted to the structure, minimizing both structural and non-structural damage. Base isolation is especially effective for critical facilities like hospitals, emergency centers, and historic monuments where functionality after an earthquake is crucial. One of the best-known examples is the Uten Research Center in Japan and San Francisco City Hall, both equipped with advanced isolator systems that have proven their worth in real seismic events. By allowing movement instead of resisting it, base isolation represents the most elegant expression of seismic design philosophy: freedom through flexibility. Energy dissipation devices, dampers that protect structures, even with strong reinforcement and ductile detailing. Not all seismic energy can be avoided. Some must be absorbed. That's where energy dissipation devices, or seismic dampers, come in. These sophisticated systems work much like shock absorbers in cars, converting kinetic energy into heat or deformation to reduce structural stress. The most common types are viscous dampers, friction dampers, and tuned mass dampers. Viscous dampers use a piston moving through a fluid like silicone oil. When the building sways, the piston resists motion, dissipating energy through fluid viscosity. These are highly effective for controlling vibrations in tall buildings. Friction dampers work by sliding metal plates against each other. The frictional resistance absorbs seismic energy, preventing excessive motion. Similarly, yielding dampers use metallic components that deform plastically under stress, sacrificing themselves to protect the main structure. For skyscrapers, tuned mass dampers (TMDIS) are massive counterweights, often weighing hundreds of tons, suspended near the top of the building. As the structure sways, the TMD moves in the opposite direction, canceling out oscillations. One iconic example is the Taipei 101 Tower, which uses a 660-ton pendulum damper to stay stable during typhoons and earthquakes. In modern design, engineers often combine multiple damping systems, optimizing them through computer simulations and experimental calibration. These devices don't just reduce damage, They improve comfort, safety, and serviceability during and after seismic events. In essence, while base isolation minimizes what reaches the structure, dampers manage what's left inside, ensuring every vibration is gracefully controlled and every ounce of energy is strategically spent. Testing the limits, shake table experiments, and real-world validation. Engineering theory means little without proof. To validate seismic designs, researchers conduct full-scale experiments using massive machines called shake tables, platforms that can reproduce real earthquake motions in multiple directions. These tests provide crucial insights into how reinforced concrete and advanced systems behave under simulated disasters. Imagine an entire multi-story building mounted on a gigantic steel platform. Hydraulic actuators below move the table back and forth, mimicking the accelerations recorded during real earthquakes, from gentle tremors to catastrophic jolts like the 1995 Kobe or 2001 Buj quakes. As cameras and sensors record every vibration, cracks, and deformation, engineers collect invaluable data about structural response, damping efficiency, and failure modes. At laboratories such as eDefense in Japan and the NEES Network for Earthquake Engineering Simulation in the United States, some of the largest shake tables in the world test everything from residential buildings to full-scale bridges. These tests don't just verify existing designs, they inspire new innovations. Through them, engineers refine numerical models, improve code provisions like IS 1893 and IS 13920, and develop more efficient reinforcement layouts and damping systems. The footage of these experiments is awe-inspiring, structures swaying dramatically yet surviving intact, proving that resilience is not about being rigid, but about being smart. Every tremor on the shake table is a rehearsal for the real world, ensuring that when the earth next roars to life, our creations are ready to endure, standing as silent testaments to human ingenuity and engineering precision. Safeguarding our future, the human impact, engineering for humanity, protecting lives and communities. When we talk about seismic design, it's not just about concrete, steel, or mathematics. It's about people. Behind every reinforced column and shear wall lies a deeper purpose, the protection of human life. Earthquakes are not just physical events. They are social catastrophes that can destroy families, displace communities, and alter generations. Every improvement in seismic engineering means fewer collapsed schools, hospitals, and homes, fewer lives lost. Imagine a family inside a high-rise as tremors begin. The structure sways, walls creak, but the building holds firm. That moment of survival is the result of decades of scientific advancement. Engineers who meticulously studied ground motion, material behavior, and energy dissipation. Reinforced concrete becomes more than a building material. It becomes a shield between humanity and nature's fury. In developing nations, where resources are limited, civil engineers face the daunting challenge of balancing safety and affordability. Programs promoting earthquake-resistant housing have already saved countless lives in regions like Japan, California, and Nepal. Each successful design is a silent promise, a commitment to safeguard not just infrastructure, but the future itself. Ultimately, the story of seismic resistance is a story of compassion expressed through precision. The buildings that endure earthquakes aren't just triumphs of design. They are monuments to human resilience, foresight, and unity. The future of seismic engineering, smarter, stronger, safer. The evolution of earthquake-resistant design is far from over. The next generation of civil engineers is pushing the limits with materials and technologies that seem straight out of science fiction. One of the most promising innovations is self-healing concrete, a material infused with bacteria or microcapsules that automatically seal cracks when exposed to moisture. This not only extends a structure's lifespan, but also preserves its seismic performance over decades. Another exciting development is smart materials, components that can sense stress, strain, and vibrations in real time. Imagine a building that feels an earthquake and automatically adjusts its damping systems to respond dynamically. This fusion of artificial intelligence, data analytics, and materials science is transforming passive buildings into active protectors. 3D printing is also revolutionizing how we construct. Entire reinforced concrete elements can be precisely fabricated with optimized geometries that enhance ductility and reduce weight, perfect for earthquake-prone regions. Combined with digital twin technology, engineers can now simulate, monitor, and update a building's structural health throughout its life cycle. Universities and research institutes worldwide are collaborating to make these technologies scalable and affordable. The dream is simple yet profound. Cities that not only survive earthquakes, but learn and adapt from each event. The future of seismic design is not just about resisting forces. It's about anticipating them, responding intelligently, and evolving stronger every time. A call to build a safer tomorrow. As this journey comes to an end, one truth stands unshaken. Engineering saves lives. The unseen heroes of civil engineering, those who calculate, design, and construct are building not just cities, but hope itself. Every beam designed for ductility, every rebar perfectly placed, is a silent guardian during nature's most violent moments. To the young students watching, your equations, models, and ideas have the power to protect millions. The future needs passionate engineers who see beyond blueprints and into the heart of humanity. When you design a structure that stands firm in an earthquake, you're not just defying physics, you're preserving futures. Let this be a reminder: safety in construction isn't a luxury, it's a responsibility. Each nation, each city, each home deserves the assurance that its foundations can withstand the Earth's fury. That's the legacy of modern seismic engineering, science serving humanity. As technology advances, may we never forget the people at the center of it all, the families who sleep safely because an engineer once cared enough to calculate a little longer, design a little stronger, and think a little deeper. So next time you walk past a concrete building, look again. Behind those walls lies a symphony of innovation, compassion, and brilliance. It stands not by chance, but by the tireless work of those who refuse to let the ground beneath us define our fate. This is the heart of seismic resistance. Not just structures that survive earthquakes, but people who thrive because of them. If this video deepened your appreciation for the unseen power of civil engineering, don't forget to like, share, and subscribe to Civil Engineering Edge. Together, we're building a community of learners, innovators, and future engineers dedicated to creating safer, smarter, and stronger structures. Drop your thoughts or questions in the comments. We love hearing your ideas for upcoming topics. Until next time, keep learning, keep designing, and remember, every great structure begins with a great engineer. This is Civil Engineering Edge, where knowledge builds the world.